knowledge of biomechanics is essential for understanding human movement, particularly within the context of sports and exercise. Biomechanics explores how the musculoskeletal system's components, such as muscles, tendons, bones, and joints, interact to produce movement. By understanding the mechanics behind body movements, we can develop safer, more effective resistance training programs and optimize the performance while minimizing the risk of injury. In terms of the skeletal musculature, movement and force generation rely on muscles attaching to bones. Each skeletal muscle must connect to bones on both ends through connective tissues to create movement or apply force. Anatomically, a muscle's origin is usually considered its proximal attachment closer to the body center, while its insertion is its distal attachment further from the center. For example, the iliacus muscle typically has its origin on the pelvis and its insertion on the femur. However, in movements like straight leg sit-ups, the femur can act as the origin due to its relative immobility. While this reversal can happen based on movement dynamics, the traditional definitions of origin and insertion maintain consistency across contexts. Muscles connect to bones in various ways. Fleshy attachments are common at the proximal end of muscles, where fibers are affixed to bones over a broad area, spreading the force applied during muscle contraction. Fibrous attachments, such as tendons, are more common. These tendons are extensions of muscle sheaths, blending with connective tissues surrounding bones. These structures create strong, stable connections between muscles and bones, allowing efficient force transfer. Movement generally involves more than one muscle. The muscle primarily responsible for generating movement is called the prime mover or agonist. For instance, in throwing, the triceps act as the agonist, extending the elbow to propel the ball forward. Conversely, the muscle that slows down or stops the movement is the antagonist. And in this case, the biceps act as an antagonist during throwing, slowing the extension and protecting the joint from excessive forces. Another important muscle role is that of the synergist, which assists the prime mover indirectly. During upper arm movements, muscles stabilizing the scapula act as synergist. For example, the scapular stabilizers assist the upper arm movers by keeping the scapula steady, enabling effective motion of the arm. Additionally, synergists are vital when agonist muscles cross two joints. Consider the rectus femoris, which crosses both the hip and knee joints. During squats, the gluteus maximus, hip extensor, must act as a synergist to balance the forces and prevent unwanted hip flexion, which could occur due to tension in the rectus femoris. When discussing biomechanics, we must also consider the levers of the musculoskeletal system. Many movements, especially those in sport and exercise, are facilitated by skeletal levers. A lever in biomechanics consists of a rigid body, bone, that rotates around a pivot point, fulcrum, when force is applied. There are three main types of levers in the human body: first class, second class, and third class levers. A first class lever is one where the muscle force and resistive force act on opposite sides of the fulcrum. An example would be elbow extension, such as in a triceps extension exercise. In this case, the triceps muscle exerts force on one side of the elbow joint, fulcrum, while resistance, like a weight, acts on the other side. Second-class levers, on the other hand, have the muscle force and resistive force on the same side of the fulcrum, but with the muscle force acting through a longer moment arm. A common example is a standing heel raise, where the calf muscles act as the muscle force to lift the body. Third-class levers, which are more common in the human body, also have the muscle and resistive force on the same side of the fulcrum. But in this case, the muscle force acts through a shorter moment arm. For example, during a biceps curl, the muscle force exerted by the biceps must be greater than the resistive force of the weight due to the shorter moment arm through which the muscle force acts. And this results in the need for greater muscle force to overcome the external resistance. The concept of mechanical advantage is critical in biomechanics. Mechanical advantage refers to the ratio between the moment arm of the muscle force and the moment arm of the resistive force. When the ratio is greater than 1.0, the muscle force required to overcome resistance is lower, providing a mechanical advantage. Conversely, a ratio of less than 1.0 indicates a mechanical disadvantage, where the muscle must exert more force to overcome the resistance. Most human muscles operate at a mechanical disadvantage, meaning that they must exert high forces to move relatively low external loads. This is why muscles and tendons are subject to high internal forces during activities like lifting or sprinting. In real-world movements, mechanical advantage changes constantly as the angles of joints and the positions of levers shift throughout the motion. For instance, during a knee extension, the patella helps maintain the mechanical advantage of the quadriceps by preventing the quadriceps tendon from moving too close to the knee's axis of rotation. This keeps the moment arm longer and helps the muscle generate more torque throughout the movement. In contrast, in elbow flexion, the perpendicular distance from the joint's axis of rotation to the tendon changes continuously, resulting in varying mechanical advantages as the arm moves through different angles. During exercises using free weights, the moment arm through which the weight acts changes based on the position of the weight relative to the joint. For example, when lifting a dumbbell, the moment arm is the horizontal distance from the center of mass of the weight to the joint axis. As the joint angle changes during the movement, the length of the moment arm and thus the resistive torque varies, requiring the muscle to adapt its force output. In resistance training, understanding these mechanical principles is crucial for designing programs that minimize injury risk while optimizing performance. Resistance exercises subject muscles, tendons, and joints to high forces, especially at mechanical disadvantage points. By recognizing the role of levers and moment arms, coaches can adjust exercise selection and technique to ensure the forces placed on the musculoskeletal system are managed safely and effectively. Additionally, an individual's unique anatomical features can affect their biomechanics. For example, people with tendons inserted farther from the joint center can generate greater torque due to a longer moment arm. However, this comes at the cost of speed because the muscle must contract over a greater distance to produce movement. These variations highlight why biomechanics is so individualized, with specific adaptations necessary based on the person's structure and the demands of their sport or activity. Ultimately, biomechanics offers valuable insights into how the body functions in motion, helping us optimize training, prevent injury, and understand the complex relationship between force, movement, and performance.